Okay, let's dive into something that's totally reshaping industries. I mean, everything from custom medical implants to rocket parts.
Yeah.
3D printing.
Yeah.
If you see the incredibly complex shapes this technology can create, you know, the potential is, well, massive.
Absolutely. It opens up design possibilities that were just way too difficult or expensive with traditional manufacturing.
Right.
But with all that amazing capability comes a really critical question. How do we know these intricate 3D printed parts won't fail unexpectedly?
Hmm.
Especially when they're made from polymers, the kind of plastics that can sometimes be a bit temperamental.
Right. Because a part that looks cool isn't much use if it just snaps under stress.
Exactly.
So our mission today is to unpack a fascinating piece of recent research shared with us, a scientific paper that really dug into exactly this challenge.
Okay.
They look closely at how damage happens and how it impacts reliability in 3D printed polymer materials using careful experiments and statistical analysis.
And we're going to explore what this paper reveals about why these printed plastics might fail, how researchers are working to predict that failure before it happens, and, some surprising insights they gained along the way.
Think of it as a shortcut, maybe, to being truly well informed about the cutting edge of making 3D printed parts reliable.
Let's get into it.
So when we talk about 3D printing here, the source material focuses on processes like fused filament fabrication or FFF.
Often called FDM.
That's the most common type, right? Where you're essentially melting plastic filament and laying it down layer by layer.
That's the one. It's fantastic for complexity, like you said, but that layer-by-layer nature introduces a key challenge. How well do those layers actually stick together?
Hmm.
This really impacts things like crack propagation and the overall strength, the performance of the final part.
And the material central to this study is PLA, polylactic acid. This is probably the plastic most people start with in FDM printing, isn't it?
Oh yeah, definitely. It's known for being pretty easy to work with and generally has, decent layered adhesion compared to some others.
Easier than some of the engineering grade stuff.
Exactly. It's very user-friendly compared to some other FDM options. The paper also touches on other common materials like ABS, nylon, and polycarbonate, or PC.
Okay.
And it highlights their different strengths and weaknesses. Like ABS and PLA are pretty forgiving to print.
Right.
ABS and PC are generally tougher. They can handle higher stress. PLA and nylon tend to be less brittle. They'll show more deformation before they actually break.
And PC is the standout for high temperatures. That's really different from PLA and nylon, which are, below 60 degrees C. Even ABS is only up to about 100 degrees C on.
That's a crucial point. Material choice isn't just about printability. It's about the environment the part will actually live in, the conditions it faces.
Makes sense.
But for any of these, understanding how they fail is paramount. And this study took a really rigorous scientific approach to figure that out for PLA specifically.
So they use a specific type of test specimen called a scent specimen. That's single-edge notch tension.
Right. Scent. And while maybe it's not the primary specimen standard ASTM uses today for measuring minimum resistance to plane deformation, things like CT or SCNB specimens are more common now for that specific measure.
Okay.
The scent specimen has a long history. It's well regarded for evaluating fracture strength. Researchers like Irwin and Kraft used them extensively back in the day.
So a tried and true method for understanding how materials break when they already have a defect, a starting point for failure.
Pretty much.
They printed these PLA samples using a specific machine, a flash-forged 3P row, using carefully controlled standard parameters, things like layer height, print speed.
And 100% infill, right, to make them solid.
Exactly, 100% infill.
Controlling those printing parameters is absolutely key. You need that consistency to get repeatable, reliable results in additive manufacturing. It's critical.
And to investigate the effect of damage right from the start, they actually introduced tiny artificial cracks manually into these samples.
How'd they do that?
With a razor blade, apparently. Just a small, sharp nick.
Okay, so they're giving the crack a head start, basically, to see how it behaves under load.
Yep. And then they pulled on them a standard uniaxial tensile test using a precise MTS machine at a very slow speed, 1 millimeter per minute, to carefully observe the deformation.
Right, slow and steady. And the critical technique they used to actually watch how the material deformed, how it stretched and yielded,
Was digital image correlation, DIC.
DSE, yeah. This involves applying a specific pattern to the sample surface, usually a white base coat. then a black spray pattern, like speckles,
Okay.
so that high-resolution cameras can track the tiniest movements of that pattern during the test. It measures the strain field across the whole surface.
Ah, so they can literally see the material stretching and, crucially, how the damage is spreading near that initial crack.
Exactly.
The source does mention this coloring was also planned for a follow-up study, but it was applied here as part of the preparation for these tests.
Yes, it's detailed right there in their method section, suggesting it was part of this test setup. And perhaps also, to ensure the coloring process itself didn't significantly alter the material's behavior under tension.
Which, as we'll get to, they found it didn't, surprisingly.
Right.
Okay, fascinating setup for the experiments. Now let's talk about the major findings. The first one that really jumps out, and it's just fundamental to 3D printing, is the huge impact of printing orientation.
Oh, this is non-negotiable in additive manufacturing. Because you're building layer by layer, the resulting part is inherently anisotropic. Meaning it doesn't have the same strength in every direction. It's weaker between the layers than along the layers, generally speaking.
Right.
So the way you orient the print relative to the forces it will experience is absolutely critical.
And this study's results on PLA really drive that home. They tested orientations at 0 degrees, 45 degrees, and 90 degrees relative to the pulling force.
And the difference was stark. Really stark. The 0-degree orientation where the filament lines run parallel to the pull.
Along the direction of the force.
Yes, that showed the highest tensile strength that took the most force to break it.
While the 90-degree orientation, with the filament lines perpendicular to the force.
So the force is trying to pull the layers apart.
Exactly. That was the weakest by a significant margin.
The paper uses a great analogy, actually. Think of supporting something on pillars.
Okay.
If your pillars are perfectly aligned with the load, that's like the 0-degree case, they're strongest. If they're angled like 45 degrees or completely perpendicular like 90 degrees, well, the structure is much weaker because the load isn't being directly supported by the strongest element.
Which is the continuous filament line itself and its bond to its neighbors.
Precisely. You're relying more on those layer-to-layer bonds, which are often the weak link.
That makes so much sense. It's not just about the material itself, it's about how that material structure is aligned relative to the load.
Definitely. And they also broke down the material's response under stress into 3 distinct zones. This shows how its behavior changes as the load increases. And importantly, how those zones shift depending on the orientation.
Okay, what are the zones?
Right. Zone I is the elastic zone. Basic mechanics here, if you release the stress, the material springs back to its original shape. It's temporary reversible deformation.
Like stretching a rubber band just a little.
Exactly. The stress range for this varies by orientation, like maybe 0 to 35 megapascals for the weak 90-degree orientation in their tests.
Okay, then zone 2.
Zone 2 is the stable plastic zone. This is where permanent deformation starts. The material stretches or deforms, and it stays that way even if you remove the load.
So it's yielded.
It's yielded, yes, but it can still carry weight. It's still stable. It hasn't failed yet. For the 90-degree, this might be around 35 to 40 MPa.
Gotcha. And zone 3.
And finally, zone 3 is the strength limit zone. This is where things get unstable. The deformation accelerates rapidly, uncontrollably, leading to abrupt, irreversible breakage. Failure.
The end of the line.
Pretty much. And for 90 degrees, that was anything above about 40 MPa. But the fascinating part is how the stress levels at which these zones occur change drastically with orientation.
Right.
The point where it enters that unstable zone 3 is much, much lower for the weak 90-degree prints compared to the strong 0-degree prints.
That truly shows how orientation doesn't just affect the ultimate strength, the breaking point, but how the material behaves all the way up to failure.
Yeah.
It changes the whole response curve.
Exactly.
Okay, so orientation is foundational. But what happens when a part isn't perfect? What about those artificial cracks, the notches they introduced?
Ah, yes. This is where the study really gets into the damage analysis, the core of it. And the first big finding here was that any initial notch, even a really small one, significantly reduced the tensile strength compared to a perfect sample with no notch.
Any notch.
Any notch. And here's the crucial, perhaps slightly counterintuitive takeaway. The strengths didn't just drop off a cliff once you had a crack. It decreased gradually as the notch size increased.
So it's not like there's some safe crack size below which it doesn't matter.
Exactly. The source is quite clear on this. It says there is no threshold below which the nick has no effect.
Wow.
Any notch, no matter how small, weakens the material to some extent. The effect might be tiny for a tiny notch, but it's there. It's measurable.
That's a really important practical point for anyone designing or using these parts, isn't it? Even minor surface imperfections, maybe from printing or handling, could potentially be starting points for failure.
Absolutely. Why does any size crack matter, though? What's the mechanism?
Well, notches, or cracks, act as stress concentration points. They create a localized area right at the tip of the crack where the stress is magnified, much higher than the average stress across the part.
Okay, so it focuses the stress.
Right. And the bigger the notch, or the sharper it is, the more that stress is concentrated at the tip,
Uh-huh.
making it the most likely place for failure to start and then spread or propagate.
Okay, that makes sense. They quantify the size of this defect relative to the sample using something called life fraction, right?
Yes,
Mm.
which is basically the crack length divided by the sample width. So a life fraction of 0.5 means the crack goes halfway across the sample.
Got it. And they saw a significant reduction in the material's remaining strength, both the elastic limit, where it starts to deform permanently, and the ultimate stress, the breaking point, as this life fraction increased.
So more crack means less strength left.
Pretty much. It confirms that as a crack grows relative to the part size, the material gets progressively weaker and also tends to fail more abruptly, becoming more brittle.
And they actually mapped out this damage progression based on that life fraction, didn't they? Identified stages.
They did. There were 3 stages observed experimentally, looking at how damage accumulated. Stage I, the initial stage. Here, damage starts and increases, sometimes with a concave curve, meaning it might accelerate towards the end of this stage.
And the starting point, the initial life fraction range for this stage, varied by orientation.
Yes, it seemed to start at slightly different initial crack sizes, depending on whether it was 0, 45, or 90 degrees. Like up to maybe 19% for 90 degrees, but a bit higher for 0 and 45.
Okay, then stage 2.
Stage 2 is the progressive stage. Here, damage increases more steadily, more regularly, across a wider range of crack sizes or life fractions. Again, the exact range varied a bit by orientation, but it covered the middle ground, so to speak.
And stage 3, the final act.
And stage 3 is the abrupt propagation stage. This is the critical phase. Damage accelerates rapidly, becomes uncontrollable, leading to sudden, catastrophic failure.
And this stage consistently began when the crack reached. What was the number?
Roughly 50% of the specimen's width, a life fraction of about 0.5.
So that 0.5 life fraction is a really key threshold, it seems.
It really appears so based on their experiments. And what's really interesting, maybe even a bit surprising, is the study found that while the damage started faster in the initial stages for the weaker 90-degree prints.
Which kind of makes sense. They're weaker overall.
Right. But the damage curves for all orientations, 0, 45, and 90 degrees, they all sort of converged right around that critical 0.5 life fraction point.
Converged, meaning?
Meaning they all reached that point where unstable failure was about to kick in at roughly the same relative crack size, that 50% mark. It suggests that once a crack reaches a certain relative size compared to the whole part, the material's likelihood of rapid failure becomes dangerously high, almost regardless of how strong the initial print orientation was. The crack itself dominates.
That's a powerful finding. That 50% mark is like a universal danger zone for cracks in this material under these conditions.
It seems that way. They also use statistical methods, like Weibull analysis.
Right, you mentioned statistics earlier.
Yeah, to model the probability of failure or survival at different stress levels for these different orientations. It adds another layer, a statistical prediction layer, on top of the experimental observations.
So beyond just observing how it fails,
Yeah.
the next step is predicting when, statistically speaking.
Exactly.
Right.
Which leads to assessing the damage and ensuring safety.
And the paper touched on different ways to assess and predict this damage. They mentioned methods like the unified theory and compared it, implicitly at least, to Miner's rule. Now, Miner's rule is a very common approach in structural engineering, isn't it? Especially for fatigue.
It is. It's a relatively simple linear damage accumulation rule, widely used. And here's a practical takeaway from their analysis. The study suggested that Miner's rule actually provided a higher level of safety in this context.
How so?
Well, their specific application of the unified theory in this study seemed to underestimate the damage compared to what they actually observed in their static tests.
So the unified theory model they used was maybe less conservative? Predicted less damage than actually occurred?
That seems to be the implication in the paper. Which means Miner's rule, being more conservative perhaps, or at least aligning better with the static damage observed here, would lead to a safer design if you used it for predictions.
So Miner's rule is the safer bet, potentially.
Precisely. Because it's more conservative and less likely to underestimate the damage, it's often preferred in real-world structural damage assessments. You want that safety margin.
Speaking of safety margins, they also mention the typical material safety factor, MSF, for PLA parts in design.
Yeah, around 1.5 to 2.0, which is another way engineers build in that necessary buffer, accounting for uncertainties in material properties, loads, and, well, potential defects.
Right. And their reliability analysis based on the ultimate stress also kind of pointed back to that critical zero point 0.5 life fraction mark, didn't it?
It did. It showed reliability dropping towards 50% right around that point, with only very slight variation across the orientations. It just keeps reinforcing the significance of that threshold.
Okay, before we wrap up, there were a couple more interesting points. One was a slightly unexpected finding about their test setup, and then a really clever proactive solution they proposed based on all these results.
Yes, the unexpected bit was about that surface coloring they applied for the DIC measurements. Remember the white base coat and black spray pattern?
Yeah, the speckle.
They actually tested samples with and without that coloring across all the print orientations.
And what did they discover? Did painting it make it weaker?
Surprisingly, no. The stress strain curves, which show how the material behaves under load, were almost identical for the colored and non-colored samples.
Really?
Yeah. This indicated that applying that thin layer of white color, which they did via colored printing in that layer, had minimal to no measurable effect on the key mechanical properties like tensile strength, yield strength, or how much it stretched before breaking the elongation, at least not under tensile stress in this study.
Okay, so the coloring process itself didn't seem to weaken the bulk material significantly. That's good to know, I suppose, if you're planning to paint your printed parts, although here it was for a technical measurement reason.
Right. It implies that, at least with this specific method and under these tensile conditions, that surface treatment wasn't detrimental to the structural performance. It didn't compromise the bulk strength.
Okay. And finally, based on all this understanding of how cracks grow, and especially when damage becomes uncontrollable, pinpointing that 50% life fraction threshold, they proposed a very targeted, proactive solution.
This was really neat. They suggest that if a crack in a 3D printed PLA part reaches around 45% of its width.
So just before that critical value 7 at 0.5 point where unstable failure really kicks in.
Exactly, before it hits the uncontrollable stage. They suggest you could intervene.
Intervene, how? Just stop using the part.
No, actually fix it, in a way, by excising the pre-cracked region.
Excising. You mean cutting it out?
Essentially, yeah. Carefully cutting out the damaged area, which would reduce the specimen's overall width slightly in that region, but it removes the defect entirely.
Like performing surgery on your 3D printed part.
That's a great way to put it. Exactly. The logic is simple and compelling. By removing the crack before it hits that critical unstable stage,
You get rid of the stress concentration point.
you eliminate the stress concentration at the crack tip, you physically halt the crack propagation because the crack isn't there anymore,
Right.
and you significantly enhance the part's expected durability and structural integrity, especially if it's operating in challenging conditions where that crack might otherwise grow quickly to failure.
That's a fascinating idea. Moving from just predicting failure or designing to avoid it to actively preventing it based on monitoring and these predicted damage thresholds.
It really shifts the paradigm, doesn't it, from purely reactive replacement towards potentially proactive maintenance or intervention for critical components.
So to quickly sum up this deep dive for you listening, print orientation. It's absolutely fundamental to the strength of your 3D printed polymer parts. Don't ignore it.
Cannot stress that enough.
Second, any crack, even a tiny one, matters. There doesn't seem to be a magical safe size below which it has zero effect. It always weakens the material somewhat.
Gradual weakening, but it's there.
Damage progresses through predictable stages as a crack grows relative to the part size, becoming uncontrollably unstable after hitting a critical threshold, which this study found to be around 50% of the width, or a life fraction of 0.5.
That 0.5 mark seems really key.
And when predicting failure or assessing damage, using conservative models, like maybe Miner's rule in this case, can offer a higher, potentially necessary level of safety compared to other approaches that might underestimate the damage.
Absolutely. Understanding these factors is just essential for anyone designing, producing, or relying on 3D printed plastic parts where performance and reliability are critical.
Yeah.
It means thinking carefully about load paths when you're orienting your print and recognizing that surface finish and minor defects aren't just cosmetic issues. They can be real structural ones.
Absolutely. So building on all that, here's a final thought for you to consider. This study points to a specific threshold where damage becomes uncontrollable, that 50% life fraction mark, right?
Yeah.
And it proposes intervening before that point by removing the defect, like that excision idea.
Right.
Given this, could predictive modeling, maybe combined with routine monitoring for crack growth, perhaps using techniques like DIC or others in critical applications, could that lead to proactive repair strategies, like the excision method they suggested, becoming a standard practice for high-stakes 3D printed components in the future?
Are we moving towards self-monitoring and repairable printed parts?
It certainly suggests a future where we don't just design parts to last, but potentially design them for monitoring, maintenance, and maybe even repair based on real-time or periodic assessment of damage. It's a really interesting direction for reliability engineering and additive manufacturing.
Food for thought, indeed. Thanks for diving deep into this research with us today.
Always a pleasure. Great topic.